Abrasive Jet Machining Part 2. This is Dr. Gurraj Singh. In this lecture, we are going to continue with the abrasive jet machining process, where in the previous lecture we have talked about the basic apparatus and the various equipment that are used up in the setup of the abrasive jet machining. This second lecture is going to focus mainly on the process parameters that are used in the AJM process. So first of all, we'll have a basic introduction of the various influencing parameters in AJM. Then we will focus on the various factors related to the abrasives, followed by the factors related to the carrier gas and the factors related to the nozzle and the jet. Then we will look at some other parameters which are influencing the various factors. And finally, we will look at the response parameters that are under observation in the AJM process. So if we talk about the various influencing factors in case of AJM, the most important factor obviously is the material removal rate, because that is the factor which is going to decide the economics of your process. If your material removal rate is high, that means your process is quicker, your cycle time is going to be lower. But again, you need to decide this on the basis of whether the surface quality at that particular MRR is of the desired standard or not. So it becomes very important here to optimize the various parameters. Now the various important input parameters or the process parameters that are considered in AJM, they are, first of all, the abrasive mass flow rate. So this is the rate at which the abrasive particles are made to hit the workpiece surface. The nozzle tip distance, this is also called as the standoff distance. There's another name for this is standoff distance. Third, we have the gas pressure. Obviously, the gas pressure is going to decide the kinetic energy that your abrasive particles eventually receive from the gas. This is the fourth point, the velocity of the abrasive particles. The mixing ratio, the ratio in which the abrasive particles and the gas, they are mixed together. And finally, the abrasive grain size. You need to have an optimal size of these grains for the abrasives. So if we take a look at the factors which are related to the abrasives, first of all, and the most important parameter here is the type and the shape of the abrasives. Now this is very important because the type of the abrasive is going to decide the MRR depending upon the hardness. So if your abrasive is very hard, it is going to fetch you a higher MRR, and if it is softer, then the MRR is going to be much lower because it is going to crumble when it strikes the hard workpiece surface. When I talk about shape of the abrasive, always we prefer the irregular shaped grits which have sharp edges. So an irregular shaped grit like this, which has these sharp edges, it is going to act as a very, very efficient abrasive. So these kind of abrasives are preferred and they tend to have a much higher MRR. And then we have the abrasive grain size. So the abrasive grain size again is very important here. If you have a larger grain size, you will have more material removal rate. But if you have a smaller grain size, you will have a lower material removal rate. But you will have a much better surface finish. On the contrary, for the larger sized abrasives, you will have a more MRR, but your surface quality is going to be very poor. And you can take a look here, the abrasive hardness. Now, if you take a look at the hardness, how it varies with the erosion rate. So as your hardness increases, the erosion rate, it tends to increase in most of the materials. For example, if you take a look at alumina, as your hardness increases, the erosion rate is also increased by alumina as well as by silicon carbide. And this is the shape of the abrasives that we were talking about earlier. The shapes which are like this, they are much more preferable as compared to these roundish shapes because they are not going to eventually cause any serious damage to the workpiece. So this type of shape is highly preferable for a higher material removal rate. Now when we talk about variation in the grain sizes, so as the abrasive grain size it improves, you can see in this graph what is going to happen. With smaller grain sizes, you will have lower material removal rates. With larger grain sizes, you will have larger material removal rates. But again, you can see that the material removal rate does not increase consistently with the abrasive flow rate, because as the abrasive flow rate increases beyond a certain value, beyond this area here, so as it goes to the right, your density of the abrasives, they are going to increase beyond a certain level as compared to this low density flow. So here the energy is directly transferred directly to the workpiece, but here the abrasives, they are going to strike among themselves because they are very large and dense in number, and as a result they are going to lose their kinetic energy here itself. And thus we see these graphs firstly increasing to the highest point, peaking out, and then they are going to fall down, because it is this stage which makes the abrasives lose their kinetic energy, and thus the force with which they hit the workpiece, and as a result the material removal rate falls. The presence of impurities, they also tend to have an impact on the material removal rate, because impurities tend to cause blockage in the pipeline, and as a result your material removal rate falls down. Next, the influencing factors related to the carrier gas. Now when I talk about carrier gas, your carrier gas pressure is something that is going to cause changes in the final abrasive velocity. So the gas pressure, or the pressure of the carrier gas, after mixing with the abrasives, is converted into kinetic energy. So obviously a higher gas pressure, it indicates a higher jet velocity. So as the pressure increases from P1 to P2 to P3, your abrasive mass flow rate also increases, and so does your material removal rate. Similarly, the gas flow rate, it basically influences the mixing ratio, and the MRR becomes maximum at the optimal value of this mixing ratio. So your MRR, it constantly increases with the increase of gas pressure or the gas flow rate. So you can see the gas flow rate here for a constant mixing ratio is continuously going to increase. Then the moisture content. So obviously the presence of moisture is going to reduce the MRR, because it is going to agglomerate the abrasive, which was discussed earlier as well, and as a result they become larger particles, and this can eventually block the pipeline, and thus the MRR comes down. Next we have the factors related to nozzle and the jet. So first of all, the inner diameter of the nozzle, well, it indicates the jet velocity for the same gas pressure and the mixing ratio. So the improper jet diameter, it can hamper the MRR as well as the surface quality. Then in case of a worn out nozzle, obviously your nozzle diameter, it increases due to wear, and as a result your surface quality tends to come down. The nozzle material, so nozzle material also has a very important impact on the final results, on the surface finish, on the material removal rate, because if your material is highly resistant to wear, then your nozzle life is going to increase, and as a result you will have better surface finish. Then when I talk about the jet velocity, a higher jet velocity can erode material at a much faster rate, but it requires a high carrier gas pressure as well. So the machine setup should have to be capable of withstanding such high pressure without leakage. So you need to have leak-proof joints within the pipings of the setup. And finally the jet diameter. So again it is same as the nozzle diameter, it is based on that, and a higher jet diameter can erode material from a wider zone. However, the accuracy may degrade, because the abrasives, they're going to become more scattered with a larger diameter. So therefore you'll have a shallower surface, and the surface quality can also decline. Next, we have the nozzle tip distance. So what is the nozzle tip distance? A nozzle tip distance, also called as standoff distance, is basically the distance that is provided between the nozzle tip and the workpiece surface. So you can clearly see here that at an SOD or a standoff distance of 1 mm, so the indentation is deeper and narrower. But as it increases, at 3 mm it becomes less deep and wider. At 6 mm it's even wider and shallower, and at 10 mm it is nearly on the surface and very broad, very wide. So the nozzle tip distance, it is the gap provided between the nozzle tip and the workpiece, and up to a certain limit the MRR increases with the nozzle tip distance. But beyond that it again comes down. Why does it come down? Because beyond a certain point your abrasive particles, they are going to again get scattered, so the MRR is going to fall. And for the optimal performance, a nozzle tip distance of 0.25 to 0.75 mm is the best possible nozzle distance. Again, this is what is being explained in the last point. So as you have a standoff distance increased beyond a certain level, first of all, your penetration or your MRR is going to increase. But beyond this particular point, it is going to fall down. So it follows a trend where it peaks out and then falls down. Next, we have the point related to the mixing ratio. So first of all, it is very important to see what is mixing ratio. So mixing ratio is the ratio of the mass flow rate of the abrasives to the mass flow rate of the carrier gas. So this is your mixing ratio. And as your mixing ratio it increases, the material removal rate first rises to a certain level and then falls down. Again, at higher mixing ratio, the mass flow rate of the abrasives becomes higher, and the same point where the abrasives strike one another and lose the kinetic energy comes into play. So as a result, the mixing ratio is usually optimized to its highest level and maintained as such. Then comes the impingement angle. So the impingement angle, again, it has been discussed earlier that it can be varied between 60 to 90 degrees, but the best results are usually obtained between 70 to 90 degrees, or rather we'll say 70 to 80 degrees is the best range of the impingement angle. Next, you have the abrasive flow rate. So as the MRR is proportional to the mass flow rate of the abrasives, as the flow rate increases, the MRR also increases. But beyond a certain flow rate, your MRR is going to fall. So as discussed earlier, it follows this kind of a pattern where it tops out and then falls down. Poor working surface condition. Well, if the surface roughness is high, then the accuracy of cut may hamper. So again, if the surface on which you're working, so say you have a surface of a rough profile compared to a surface of a planar profile. So in case of your rough surface, the MRR is obviously going to increase, but the accuracy may fall. But in a much smoother surface, the MRR will fall down because the abrasives will have a tendency to strike it and bounce back, which will not be there in case of this particular case where you have a rough surface. So both these cases have their own pros and cons. In one you have a better MRR, in the other you will have better accuracy. Inhomogeneity of the material properties. So this also may result in inaccuracy. Stress concentration can also have an effect on the MRR by reducing the erosion rate. So finally, what we conclude is that these are the most important parameters related to the various factors. So first of all, you have the abrasive related parameters, the material of the abrasive, the shape of the abrasive, the size, the variation in size, the strength and the flow rate. When we talk about the carrier gas, you have the nature, the composition, the pressure, the flow rate and the temperature of the carrier gas. When we focus on the abrasive jet, you have the velocity of the jet, the mixing ratio, the impingement angle and the standoff distance. And when we focus on the work material, you have the properties of the work material, the induced stresses and the inhomogeneity. So these are the most important influencing factors in abrasive jet machining, and each of these you can keep all of them constant and vary just one. For example, you can just vary the mixing ratio and keep the rest constant. Your results will vary. So on the basis of these varying parameters, you can have n number of results, and this opens up a huge scope for optimization of these parameters and getting the best possible results using a specific material for both the workpiece as well as the abrasives. Then you have responses for measuring performance. So the basic responses that we have are material removal rate. So this is the most calculated response parameter here. Then you have the surface finish, and finally the nozzle life. So these are the three responses that are talked about in abrasive jet machining. Now when I talk about the process parameters, well, abrasives, mostly the materials that we use as abrasives, they are either alumina or silicon carbide. Their shape can be either irregular or spherical. Their size can vary from 10 to 50 micrometers, and their flow rate can vary from 2 to 20 grams per minute. When I talk about the nozzle, the material of the nozzle can usually be tungsten carbide or it can be sapphire. The diameter, the internal one, is 0.2 to 0.8 mm, and the life can vary from 10 to 300 hours. Then you have the carrier gas. So the composition of the carrier gas, normally air or carbon dioxide or nitrogen. The velocity is from 500 to 700 meters per second, while the pressure is maintained at 2 to 10 bars, and the flow rate varies from 5 to 30 liters per minute. When we talk about the abrasive jet, the velocity of the jet is normally from 100 to 300 meters per second, while the standoff distance is varied between 0.5 to 5 mm, and the impingement angle, it varies from 60 to 90 degrees. Now when we discuss the mechanism of material removal in abrasive jet machining, it is simply microchipping or brittle fracture. So the abrasive particles hitting the workpiece at a higher velocity with a higher kinetic energy, they tend to have microchipping performed onto the surface and the material gets machined off. So this was all related to the parametric studies concerned with the abrasive jet machining, and in the next lecture we will discuss about the mathematical modeling of the abrasive jet cutting and the various numerical problems related to that. Thank you.